Okay, so I posted Wednesday's homework. That will consist of web work. You should do that first. Get to do the web work first. And then I put the final version of the written homework. So you got lots of questions. Hopefully you've already started, but you do have 5 days from now, okay? So when you do that will be due in class on your own paper. And then a part of that grade will be, like I said, for professionalism, completeness, using full sentence explanations. Whenever it asks you to explain something, you got to write it out. Write out what you're thinking, okay? If you just jot down phrases, that's not sufficient, and you'll get marked down, okay? So and make sure it's a professional presentation, okay? Neat, organized, readable, etc. Okay, and then just don't forget I changed the wording on the questions on number 30. So we'll hand that in at the beginning of class on Wednesday, and you'll also have web work. And then that I had told you that there's this tutor center. It's designed specifically for our class, for our Pathways curriculum, okay? So the people that are in there have at least some training in the curriculum. Most of them have a good amount of training, okay? But everyone's been trained in this curriculum. Some of the tutors you may have better luck with than others. So just keep coming back and try to find the ones that you find are helpful. It's not perfect in there. It's not perfect, but we are doing our best to train those tutors in this curriculum. It's in PSA 21. That's the basement. It opens the 2nd, and so it's going to be 9 to 6 Monday through Thursday and 9 to 1:30 Friday. So if you want help on Tuesday, it'll be open all day Tuesday. I also have office hours Tuesday. You can check that out. And then eventually Jerem will know his hours. That's where he'll hold his office hours in that tutor center, and we'll tell you exactly when those are. Okay, questions about homework or the tutor center? So this now starting Tuesday, it'll be open every day of the week, Monday through Friday, and that's a great resource for you. Okay, and you can just go there and just work on your homework. You don't have to have a question, but then you can get help if you need it. Or you can just bring your questions, get them answered, and leave. It's come and go as you please.
Is it that testing center?
Yes, it's where if you've been to the math testing center before, that's the tutor room for us. Okay, so that's the same as if you've been to the math testing center in the basement.
Did I get everybody's quizzes?
Quizzes are due. Take home quizzes. And then when you get a chance, if we could turn the front lights off.
Oh, sure.
Yeah.
I think I remember which one that was.
Okay. Other questions on stuff like that? Okay, so we are talking about. Oh, I did want that. We're talking about constant rate of change. Too much. Yeah, way too much. Can you just control the front? That's okay, that's good.
That's good?
Yeah.
It'd be nice if they were labeled.
Yeah. Okay, so we are talking about constant rate of change. And as you're seeing in these problems that we're doing in class and your web work, it's like the days of y equals mx plus b are long gone. Okay? So we're much more interested in getting in depth what's really going on and thinking about all this in a dynamic way. As one quantity changes, how does the other change? So we're thinking about two quantities changing together, okay? Which is worlds different than, find m, find b, write the equation of the line, right? So that's totally different. So this is what we want to focus on. How do linear relationships reflect how two quantities change together? And that's constant rate of change. So we said constant rate of change is about the changes in the quantities are proportional. Changes in the quantities are proportional. That's kind of the equivalent of saying constant rate of change. Okay. So here's the deal. Constant rate of change means changes in the quantities are proportional. And we said at the end of class last time, and you practiced a little bit in your homework, there's 3 implications of that. 3 mathematical implications of that if the changes in quantities are proportional. The first was, equal changes in one quantity result in consistent changes of the other. So every time you change x by 5, you're going to get the same, some change in y that's always the same, no matter where you apply that change of x of 5. If you change x by 0.2, 0.2, you're going to get some change in y. And no matter where you apply a change of x of 0.2, you'll always get the same change in y. That's the first one. Second, the change in one quantity is a constant multiple of the corresponding change in the other. So if you want to know a certain change in y, and you know you have constant rate of change, well, you know that's going to be some constant multiple times the corresponding change in x. And then the last one is that the corresponding changes in the 2 quantities maintain a constant ratio. Delta y over delta x is constant for any corresponding pair of delta y and delta x. Okay, is this familiar? Does this feel like a review from Wednesday and from the homework? It should. But crucially important. When you're solving all these problems involving lines and linear equations and constant rate of change, practice this kind of thinking. We're going to do it some more today. But practice applying these principles whenever you have a situation of constant rate of change, because that's what you're going to be responsible for understanding. So let's see this kind of visually, okay? Let's see these three implications of constant rate of change. Let's see it visually. So the first one, equal changes of one quantity result in consistent changes of the other. So if you pick a delta x, any delta x, a small delta x, a large delta x, and you repeat it, so we have equal changes in x, always result in consistent changes in y. Makes sense, right? And that means that rate of change is staying constant. That rate of change is staying constant. Okay? The change in one quantity is a constant multiple of the change in the other. So here's now 3 different changes in x, giving 3 different changes in y, right? But every one of those changes in y is some constant multiple, let's call it k, times its change in x. So you just, the proportionality of the changes, right? Proportionality of the changes. If you expand delta x by something, delta y gets expanded by the same amount. Okay, so this is a really important idea, that changes in y are a constant multiple of the changes in x. And then looking at that same picture, the corresponding changes maintain a constant ratio. So delta y1 over delta x1 is the same as delta y2 over delta x2, is the same as delta y3 over delta x3. And that stays constant. Okay, and then that value, that ratio, which we're calling k here, that is the value of the constant rate of change. So remember we said this phrase, constant rate of change, kind of has 2 meanings. The first meaning is it's just the general principle, right? The principle where you have proportionality of the changes. But then also this phrase, constant rate of change, means the number, that constant ratio that you get when you divide delta y by delta x. That's called the constant rate of change, the number. What does this have to do with slope? How do you calculate slope? Okay, so remember, so you had 2 points, and what did you take? You took y2 minus y1, remember this? Over x2 minus x1. Well, what is y2 minus y1? Delta y, right? We said you take the final value y minus the initial value y. You get delta y. Similarly, x2 minus x1, delta x. So what is slope? What is slope? It is the constant rate of change. Okay, so it's not about inclination of the line, because I can change the scales and I can make a line with the same constant rate of change have any inclination I want by messing with the scales on the graph, right? Like if I zoom out on the x-axis or zoom in on one of the axes, it's going to change the inclination of the line, but it doesn't change the constant rate of change. Okay, so slope. Don't think of slope as how the inclination of the line or how steep it is. Why? Because for the same slope, you could have lots of different. You could manipulate it to show a different steepness. So now instead, think of slope as the constant rate, right? So slope just is another word for the constant rate. But it's not a crock, right? It's constant rate of change. Questions on this review? So let's practice some more, because this is, for most of us, this is the first time we thought about linear relationships with all this stuff about the changes, right? And the proportionality of the changes. So let's practice. So I have an example here. So the green is this problem setup. Okay, a soldier lowers an American flag from the top of a flagpole that's 14.5 meters tall. Okay, the blue, everything blue is your tasks. These are your tasks that you're going to do. I'm going to take attendance here in a second. You're going to start working through these tasks. Task number 1, you're going to define 4 variables using the criteria we've been working on to define variables. T, H, delta T, and delta H. That's number 1. Number 2, I'm giving you, so here's the data for corresponding values of time gone by and the height of the flag. And I'm giving you also values of delta T. So in number 2, you're going to come up with intervals that have those delta T values. Does it make sense? So you're going to look over here at you're going to find some interval of time that's 1.5 seconds, and then write down the starting and ending values of T. And you're going to repeat that 3 times for 1.5, a couple times for 3, a couple times for 5, and for 10. So you're going to fill in values of T that give these changes in T. That's number 2. Then number 3, you're going to find the values of delta H. Okay? By looking at how H changed when T changed the way you picked. So people are going to have different responses here. People are going to have different responses. That's number 3, find delta H. And then number 4, in this context, what 3 questions can we ask? Once we filled in all the tables, what 3 questions can you ask to determine if H varies at a constant rate with respect to T? Any of those 4 tasks that are not clear, you have a question. I'm going to start taking roll, and you're going to put you to work. I'm going to put you to work. So are we good? You can work together, share what you're thinking. If you have a question, Jerome can help you out also. Okay, go. Okay, check your variable definitions. They should be, if not the same, very close. You should have all the same elements. Here's the 4 variable definitions.
Oh, that's just
Time elapsed in seconds since the flag began to be lowered. Something like with that much detail, okay? Height of the flag above the ground in meters. Change in time elapsed since he started lowering the flag. Change in height of the flag above the ground in meters. Those are your 4 variables. You should have that much detail. It could be worded a little differently, but that much detail. Yeah, we're about to start, yeah.
oh.
It's like spinning a wheel. Where's Jonathan Mack? Jonathan Mack. Can you tell me, did you find an interval that has a change in time of 1.5 seconds? What'd you say? 2 to 3.5? And as t changes from 2 to 3.5, what does h change from, Jonathan? From what to what? Where's Mitchell? Mitchell, as t changes from 2 to 3.5, what does h change from what to what?
12.1 to 10.3.
Right. So as t changes from 2 to 3.5, h changes from 12.1 to 10.3, and what is that change in h? Did you get that?
Negative 1.8.
Negative 1.8. Mitchell, did you find another time change of 1.5?
3.55.
And what does h change from as t changes from 3.5 to 5?
Negative 1.8.
So from what to what?
10.3 to 8.5.
10.3 to 8.5, which you said was?
Negative 1.8.
Negative 1.8. BJ, tell me, did you find another time change of 1.5? Give me the starting and ending time of another time change of 1.5. 5.5 to 7. And what does h change from? From what to what?
7.9 to 6.1.
Good, right? So from 5.5 to 7 is a delta t of 1.5, where h changes from 7.9 to 6.1, and what is delta h? Negative 1.8. Okay, cool. Alexis. It's like spinning a wheel. I like it. Alexis. Change of 3. Did you find a starting and ending time change of 3, Alexis? Where's Alexis? 5.5 to 8.5. Corresponding change in h. 7.9 to 4.3, a change of h of? So how much does, what's delta h when you go from 7.9 to 4.3? Negative 3.6. Okay? Running out of space here. Okay, with this. Fahia. Another change of time of 3. From what to what? Good. 7 to 10. Delta H in that case? Did you say negative 3.6? Okay, Eitan. You're up. Another change of, or a change of 5 this time. Did you find a change of 5?
5 to 10.
5 to 10? What was delta H in that case? Minus what?
8.5.
Minus 8.5? Minus 6? Minus 6. Michaela, another change of 5. From what to what? 2 to 7. Good. Delta H in that case. So we're going from 12.1 to 6.1. Negative 6. Finally, change of 10. There's lots of, how about a Nick? Or Walter, go ahead. Walter.
0 to 10.
0 to 10.
And the changes are from 14.5 to 2.5, so it's
12?
yeah, negative 12.
Negative 12. So your table should be similar to this. So you could have for the first entries you may have in a different order, you may have different choices, but here's the general idea. Questions on what we've done so far? Okay, so what about, now we've got all this data and we want to ask, is t, or is h changing at a constant rate with respect to t? So we want to look at our 3 perspectives on constant rate of change and test all of them, just for practice, okay? So what's one of the perspectives, or one of the questions we can ask to determine if h varies at a constant rate with respect to t? Tell me, what's your name? Adam.
Is delta H constant ratio of delta T?
Okay, are delta H and delta T in a constant ratio? And in fact, that's the first one I have too. No, that's not the first one I have. Anyway, so let's talk. So there's that one. There's that one. Do equal changes in T result in consistent changes of H? There we go. That's the second one. So Adam said this. The one I have is second. So while the first one is up there, let's ask that question. Do equal changes in T result in consistent changes of H? Or do we have evidence of that? Yeah, every piece of evidence we have says yes to that. So now, it's not proof, right? Because we could, to really prove this, we'd have to pick every single, say, change in T of 1.5, which is, there's an infinite number, right? And we have to prove that every single time you get negative 1.8 for the change in H. Okay, so it's really kind of an impossible thing to prove, this question. But all the evidence points at it. All the evidence that we have points at, if you change T by a certain amount, you're always going to get some consistent change in H. All right, now the second one. This is what Adam said. Do the change in H and change in T maintain a constant ratio? Well, in order to do that, we need to find the ratio. Okay, so what's one way we can look at the change in H, find that ratio, change in H over change in T? Nice. Okay, so we're looking at change in H divided by change in T. And he said you could do negative 1.8 over 1.5. What do you got? Negative 1.2. So does that calculation right there tell us constant rate of change? No, what else do we have to do? We have to try other ratios, right? So no matter what delta H and delta T are together, they always have to give this ratio if it's going to be constant rate. So what's another ratio we're going to test? Negative 3.6 over 3. And then? Negative 6 over 5. And finally, do all those equal negative 1.2? Yes. So as I'm guiding you through this may seem incredibly easy. Does it feel easy? But here's the thing that's more difficult. If I just gave you the green statement and this table, could you do this analysis yourself? Could you come up with this? Think to write down changes in T. Think to write down the corresponding change in H. Think to set up these ratios. That's what you have to be able to do, instead of having someone hold your hand through it. So when someone holds your hand through it, yeah, it seems really easy. But you're just going to, in homework, you're just going to have a situation. Can you perform this kind of analysis? Can you generate it yourself and do this kind of stuff?
We have to do the 3, 2, 1. Like they have 3, 1.5, 2, 3, 2.
No, that was just the table that I came up with. Yeah, so you would check as many ones as you're to convince you. Yeah, but there's nothing magic about the yeah, that was just,
as long as we get the same.
yeah, so you're checking enough of these ratios to convince yourself that ratio stays the same. Yeah. But there's no the way I set up the delta T table was I just picked some way to do it, okay? All right, what about the ratio of H to T? So we're doing change in H to change in T. What about, let's make a new column here, and let's do just H over T. So how about for this one here? Let's just do 2 examples, and this one here. So you do that. So for T equals 3.5, find the ratio of H over T. And for 8.5, find the ratio of h over t. Go.
Did you say 3.5?
I put the arrows there, yeah. 3.5 and 8.5. Is that right? A7 over B7? No, what should it be? B7 divided by A7. I got 2.943. And then I got 0.506. Okay, so question. Do H and T maintain H over T, do they maintain a constant ratio? No. Okay, so are H and T, is H changing at a constant rate with respect to T? Is H changing at a constant rate with respect to T? Talk to the person next to you. Go. Is, not just say yes or no, but why? Why? Yes or no and why? Go. Okay, I want to hear some different thoughts here. So volunteers, do you think H is changing at a constant rate with respect to T? Yes or no, and why? Is that a hand? Go for it.
All right, so H is changing at a constant variable.
You say yes or no?
Yes.
He's saying yes. Why?
Well, that equation there, H over D, doesn't represent the rate of change relative to each other.
Okay.
It represents actual values.
Okay.
So it's doesn't really matter if those aren't constant. And what is constant is what we have there, the rate of change.
So he's saying this ratio doesn't matter. For constant rate of change, what really matters is the ratio of the changes. Somebody else? Yes, sir.
I just agree with
You agree with him?
it. We're talking about the change, so the actual measurement of the height and the actual measurement of time is irrelevant.
Okay.
If you're talking about a constant rate of change, that's what
Good. So are we talking about the constant rate of change of delta H and delta T, or the constant rate of change of H and T? H and T. We're asking if H and T are in a constant rate of change relationship. In order to check that, we look at what ratio? The ratio of the changes. Okay? Exactly what he said was right. The ratio of the actual values is not our check for constant rate of change. It can change. That ratio can change because what? Time is going up and height is going down. There's no way that ratio is going to stay the same. But the ratio of the changes, how much delta H changes when delta T changes, that's always negative 1.2. And by the way, negative 1.2, what unit is that? Feet per second, some people are saying. That's right, feet per second. Meters per second, sorry. Meters per second. So what is that? So when we say constant rate of change and we're talking negative 1.2 meters per second, what's the meaning of that, negative 1.2 meters per second? Yeah.
Speed at which the flag is going down.
Yeah, it's going down. And is that speed changing or staying constant? Staying constant. Every second, it's going down negative 1.2 meters. Every 10 seconds, it's going down how far? 12 meters. Right? Every 5 seconds, it's going down how far? 6 meters. This is constant rate of change. So we're checking the constant rate of change of the quantities H and T. We do that by investigating the changes in the quantities. The ratio of the actual values may or may not stay the same. And in this case, it can't because the one's going up while the other's going down. Okay, what's the last check for constant rate of change? So the first two checks definitely point to constant rate of change. We got equal changes, consistent changes of height for equal changes in time. we have a constant ratio of the changes of h and time, or yeah, h and t. What's the last thing? What's it? Is t a constant multiple of h? The change of t. Right, it's about the changes. Actually, we want to know if the change in height is a constant multiple of the change in t. So now we're looking over here at the table and we're saying, is there some number that we can multiply the change in t by to always get the change in h? So, is there some number that will always do it? Given the change in t, will give us the change in h. Is there a constant multiple? And what is the constant multiple? The constant rate of change. That constant multiple is the constant rate of change, the ratio of delta h to delta t. Negative 1.2. Etc. No matter what delta t is, you multiply it by negative 1.2, gives you the change in h. Okay, so let's graph it. Okay, so here's the raw data of time on the x-axis, or the horizontal axis. Time in seconds. And on the vertical axis, we got our h in meters. And so because we have constant rate of change, what is our graph? What is our graph? Right, so it's going to be linear because, say, for every equal change in time, so let's show the change in time of 1.5. There's a change in time of 1.5. How much does the flag go down? What did we find? Oh, sorry. So then down here later, starting at 7 seconds, when 1.5 seconds goes by, how much does the flag go down? Negative 1.8 again. Equal changes in time result in a consistent drop in the height of the flag. Okay, is this all the points? No, there's lots, right? So there's a point for any, there's an infinite number, right? For any point in time after the flag starts to be lowered, we can get a point. Okay, so graphing all the points. Something like this. Also all the way up there. I don't know why I didn't do it. So when you look at that black line, what do you think? Points. The emergence of those points shows how the height changes as the time changes, right? So thinking about those points emerging as time continually increases, just think about all those points, shows the relationship of these two quantities, right? And this particular relationship is very special because it's constant rate of change. Constant rate of change. Okay, what's the equation of that line? H equals what? So we want to write H now in terms of T. How would we write H in terms of T? Everyone do it. Everyone do it however you can. However you can do it. Write H in terms of T. Someone, tell me your name in the red shirt. No, yeah, in the red shirt, yeah.
Oh,
What's your name?
Daniel.
Daniel. Did you get something?
Yeah, h equals negative 1.2t plus 14.
Negative 1.2, and tell me your reasoning behind that.
Because, like, let's say you just have h equals negative 1.2t. If you put 0 seconds, it doesn't start at 0, so it's at 14.
Starts at 14.
So that's the y-intercept,
Okay.
basically, and it constantly goes down 1.2. So
Every what?
every
Per second, right. So he's saying when t is 0, we need to be at, is that right, 14? 14.5. And then for every time, for every second that goes by, that 14.5 is going to go down by 1. So we got our starting value. And then what is negative 1.2? It's the constant rate of change. Should make sense. So if you had 14.5 minus 1.2t, that's the same thing, right? Negative 1.2t plus 14.5 or 14.5 minus 1.2t. Questions on this example? So like I said again, when you're doing all these problems in the homework, practice all this type of thinking and reasoning that we're doing, because that's people that can walk their way around a problem this way know worlds more than people that can just set up y equals mx plus b. Okay? And it gives you tools to analyze all kinds of situations. So let's look in your book. I've got an example queued up here. What page of your book is this example? It's Investigation, Module 2, Investigation 4, number 2. Page 35? Page 35. Okay, so I'm gonna go a little bit faster here because we got 5 minutes, and I want to get through lots in this problem. So just really try to tune in. So here we go. It says that the candle decreases at a constant rate of 2.2 inches per hour, and the candle's been burning for 3.5 hours, and it's currently 8.3 inches. Okay, represented by that point right there. So you've got you can see the x-axis in your book. I'm not really showing it here. Okay. So it talks about a change of, starting here at 3 hours, a change in time of 2 hours, right? Is that the question? Let's say a change in time of 2 hours, like part B or something? Okay, how can we so we're right now at time 3.5. How can we represent a change in time of 2 hours? Yeah, I'm going to need that. Let's see. There we go. So he wants me to draw a horizontal line for 3.5, starting there, to like that. And that blue segment right there represents what? Delta x equals 2. Okay, so this constant rate of 2.2 inches per hour. Based on all this conversation we had on the flag and all this stuff we're talking about, but tell me more about that. So constant rate, it's decreasing at a constant rate of 2.2 inches per hour. What is that? So tell me anything that you know. Somebody new.
It's a speed.
Okay, it's a speed, but relative to our conversation, what's that? It's t? It's t. It's a value of t. 2.2 is a value of t. Agree? Who said no? Kenneth, right?
Yes.
What do you think the 2.2 is?
It's how much the candle is losing per hour, so how much is going down.
Okay, so could you it's how much is going down. So could we say, could we write something symbolically that would be the 2.2?
So maybe like -2.2.
Negative 2.2? So symbolically, how can we represent that in this situation?
Delta y represent x equals change.
Delta, okay,
Delta y over delta x.
yeah, is that what you're going to say?
No, I was going to say h equals -2.2t.
H equals negative 2.2t. Careful. But a lot of people are saying this. They're saying delta y over delta x. What do you think?
Yeah.
That's right. Okay, we know that's if it's the constant rate of change, it's our constant ratio of the change in y to the change in x. Okay, and if that's our constant rate of change, then given a change in x, how could we find the change in y? This is another perspective on constant rate of change. So given it, yeah.
Okay, Nike times delta x to the other side, so delta y equals -2.2 times delta x.
But you didn't even need the algebra too, because this is one of our perspectives on constant rate, right? That if you have a change in x, it's a constant multiple of the change in y. Remember that? So this is changes maintain a constant ratio. The change in y is that ratio times the change in x. So now I'm going to use this fact right here to find what's the corresponding. So if 2 hours went by, what's the corresponding change in y to those 2 hours going by? And how'd you get that? Yeah. 4.4? Negative 4.4, so. 1, 2, 3. So delta y will be negative 2.2 times what? The change in x, 2, based on that thing. And so then how would we get the new value of y? So now we've got some coordinates at that point. So the time was 3.5 and 2 hours went by. So what's the new time? 5.5. And the candle was 8.3 inches tall, and it went down how much? It went down 4.4. So the new y equals starting y plus change in y. So the new y, so it was the starting y, 8.3. The change in y was negative 4.4. So this is 8.3 plus negative 4. This should make perfect sense. The new value of y would be what you started with plus how much it changed, right? And that ends up being 3.9. So we're using all this stuff to analyze the situation. We're using all this stuff about constant rate to analyze the situation.